Hi, this is Harmonic Motion Part 3 for Physics 1, and we left off with the wave motion. So if we think about it, if we throw a rock into a pond, we see this ripple effect. I'm sure we all have kind of done this. And what we're going to look at is the water itself is what we'll call the medium. And then we can see that waves sometimes will move through different materials or different mediums, and some waves will move through no medium whatsoever. Right? And so, as this rock hits the pond, it has a certain amount of energy, and it's going to impact the water with that energy and create an impulse. And that impulse is basically creating a force inside the water, and then that force will carry through and carry out in all directions as the impulse transfers from one particle of the water to the next. And so the energy is transported across the water in all directions, and so we see this wave pattern as that energy moves across the water. What's actually happening is the particles, we can see this as a rope or even as the water down here. The particles are actually just moving up and down as they get disturbed with this energy. But then the energy transfers to the next particle and so on. And so what we find is we can measure the velocity that it takes for this energy to kind of move across. And we find that the velocity is equal to the frequency times what we call the wavelength. And the wavelength for any wave, and we can look at it as a sine wave or even a cosine wave. I do both. Okay. The wavelength is basically how long does it take, or how far does it go before it repeats. So what is this distance, right? Or what is this distance? Now if we extend this to multiple waves, cycles, I'll do a second cycle, right, where this is the beginning part of the next, and I didn't draw it that great, but these should be the same. The wavelength is going to be any spot that goes with one spot of this cycle to the spot in the next cycle. So we can actually get the wavelengths from just the top crest, okay, or just the bottom crest. And the same thing here if we continue. To draw this, the top crest from one hill, top hill, to the next top of the hill is the wavelength. And wavelength is measured in meters. Frequency is 1 over second. So actually, if we wanted to write this as the period, we could write it as wavelength over the period. And what we have here is meters over seconds, which is this distance over time. So that's all this velocity equation is distance over time. So if we're looking at a fisherman and he notices the crest past the bow of his anchor every 3 seconds, okay, so as this waves moving across every 3 seconds, you get a top of the wave passing. He measures that distance between those crests to be 7 meters, and he wants to know how fast the waves are traveling. Right, so we actually have it set up already. Velocity equals wavelength over time. The wavelength is 7 meters, distance from crest to crest. and then 3 seconds. So 2.6, I'm sorry, 2.3. 33 meters per second. Alright, so there's a couple types of waves. We have what's called transverse waves. You see these mainly in physics 2 if you take it. It's I don't know why I scrolled over. Transverse wave is something like light, and it's pretty much a movement of up and down. And so how we would think of a wave, normally how we would draw one would be a transverse wave. The particles move up and down as it moves across. So the particles movement is actually opposite to the actual movement of the wave. And so this transverse wave is going to be dependent on its material, its mass and length. And then it's going to be dependent on the tension in the material. And so we can actually find it by velocity is equal to square root of the tension times the length over the mass. Right, and so that's one of the waves you'll get into in physics 2. The next type is longitudinal wave. This actually is sound type waves, and they move back and forth, kind of like a spring will move back and forth. And you'll see there's parts where the spring's stretched out, parts where the spring's compressed. And so the wavelength will consist of one part stretched out, one part compressed. Okay, the stretched out we call rarefaction, and then the compressed we just call compress. And so we do have a wavelength within this type of wave itself, even though it's harder to see because of the way it is. But the particles travel through back and forth as it goes through the medium. And so there's two things we look at here. We look at whether this material is a solid or a liquid or gas. If it's a solid, then the velocity is just the square root of the elastic modulus of the material divided by the density of the material. If it's a liquid, the velocity is the square root of the bulk modulus of the material divided by the density of the material. Okay, and then in both of these waves, what would actually start the waves would be some initial pulse that puts energy into it, and then you have the wave. So for instance, sound, just making a sound some way is that initial impulse. For light, it may be something like turning on a light, I guess. When you have something start to glow, that's your initial impulse. And so we're going to do examples of each here. Yeah, I'm almost done with the video, Rachel. I'll give you breakfast here soon.
I tried finding flashing from the tub.
They're in the bedroom. Yeah, on the black shelf. All right. Sorry, it's morning. My daughter just woke up. All right, so for this example, we have a cord stretched between two supports. So I'll kind of draw it. So first support, some cord stretched between the next support. Cord is 40 kilometers, 0.4 kilograms. And the distance is 8.7 meters apart. You strike a support with a hammer. The hammer then it strikes the support, and it sends a wave down through this cord to the other support. And that wave, we measure the time, and the time it takes to reach the other side is 0.85 seconds. We want to know what tension is. Okay, so we actually have the speed here. Right? We know speed equals the square root of FTL over M, but we have the speed, so we gotta find the tension. So I'm gonna solve this for tension, and then we'll plug in the numbers. So I'm gonna square both sides. Then multiply by mass, divide by L. So mv squared over L. And that's now our equation for our tension. Now the V, we can find that is just going to be the length of your distance as traveling. So 8.7 divided by 0.85. Right, so mass is 0.4. Speed is 8.7 divided by 0.85 squared. And then the length is 8.7. Alright, excuse me 1 second. I don't know if you could hear that. My daughter had a tablet blaring. It's not distracting me. Okay, so when we plug this in a calculator, we end up getting, let me plug it in real quick, 8.7 divided by 0.85 squared times 0.4 divided by 8.7. We get 4.82. And that will be your tension. So for the longitudinal wave, a sailor strikes the side of a ship just below the surface of the sea. He hears the echo of the wave reflected from the ocean floor directly below 2.4 seconds later. And he wants to know how deep the ocean is. Right, so here's the little boat, and he sends a sound wave all the way down, which that's the sound wave. I can't really draw a longitudinal sound wave that well. And it strikes. And the time it takes is 2.4 seconds. And it takes some distance. I'm gonna call it X. Some distance X, where X is going to be how deep this ocean is to get down to that point. Now we know velocity equals, since we're dealing with a liquid, the bulk modulus over the density. Right? These are just two constants for that liquid. So it would be bulk modulus is 2 times 10 to the 9th, and then the density of water is 1.03 times 10 to the 3rd. Right, and so this is going to equal your speed, which comes out to be, actually, let me do it on a calculator. 2 times 10 to the 9th divided by 1.03 times 10 to the 3rd square root comes out to be about 13 93.47. And so that's the speed it takes to get down to there. Now what we need to do is figure out, well, what's the distance? So, one thing I should have mentioned this. He's hearing this 2.4 seconds later. That's the time it takes to go down and back up. Right, because he's going to hear it after it echoes off the floor. So we can also write your velocity here as 2x. That's your distance over that time. Right, and so that 2x over t equals 1393.47. So we solve for x. So x is equal to 1393.47 t over 2. So 1393.47 times the 2.4 over 2. And you get 1672. Okay, so roughly about 1700 meters down. Let me check the time on this. Okay. The next thing we'll get into is what's called resonance, and then we'll get into standing waves. I'm not sure if we'll end up finishing this in this video. I don't think so. I think I'm going to do one more video after this. Alright, so with resonance, because we have the period of some object is 2 pi square root m over k. Okay, we can think of this as whatever, some object and with some spring constant, and then we know that the frequency is 1 over 2 pi square root of k over m. Well, this means that every object has its own, what we call natural frequency. This is the natural frequency. And then if some object is forced to vibrate at that frequency or a multiple of that frequency, you end up getting what's called resonance. And so you get a increased amplitude of this wave. And so we can actually see this with large objects that end up having large forces applied to them, and you get a natural frequency being something driven at its natural frequency, and you get raising your amplitude. For instance, this bridge in this picture, the earthquake caused it to kind of vibrate at its natural frequency, and the road went up, and kind of built kind of this wave-like pattern a little bit. And this is, of course, due to the vibrations within inside any material. Right? And so when you have resonance, you have this vibrating system of the material and an external force causing it to vibrate at that frequency, and you get a greater amplitude, especially if it's sound. You get a greater amplitude. For instance, a swing will go higher when the force is in phase with the swing. Light would be brighter, things like that. Alright, so we kind of use that a little bit when we're dealing with standing waves. And when you're looking at standing wave, you're going to have a couple things here. You're going to have what's called nodes, and this is the point of zero displacement. So nodes are where, if this was normally a straight line, and here we're looking at, let's say, a chord fixed on both sides. Okay, if this was a straight line, anywhere where that line stays, that point stays the same, is what we'll call a node. So each of these are node. With that point, that particle in the sense of that material did not move up or down. And then the max displacements are the antinodes. So these are antinodes. And these are nodes. And so then when it hits the other side, it's going to reflect back. And you see kind of the opposite pattern go all the way back. And then it just continue. So you do the green again and the red as it reflects back. And this is what we call a bound system, when it's fixed on both sides. Okay, and so we consider the endpoints to be nodes as well, since they are fixed there. Which means any wavelengths have to always end with a node on this side. So if we think about it, if these have to be fixed, we could have as low as 1/2 of a wavelength. So this is 1/2. Where the other half is the downward spot of this. That's not part of this. Okay. So we can have 1/2 wavelength. We can also have a full wavelength. And then we can have 1 and 1/2 wavelengths. And then we could have 2 wavelengths. And so on. So what we do is we look at these as each kind of different harmonics is what we'll call them. The first one is a fundamental harmonic, or the first harmonic, and each one of these after is overtones, and so it'd be second harmonic, third harmonic, and so we can name them with a letter N. So here the N equals 1, this one N equals 2 for the second harmonic, and then the picture we had over here, well, kind of down here, this is N equals 3. And so what we can write is we can write the wavelength in terms of N, and in terms of the length of the actual chord here. So to get this chord, we would have to have twice the chord to make one full wavelength. And so this is 2L over the first harmonic. We can think of this as, if we flipped it, the length of the chord is going to be 1/2 the wavelength. And so if we solve for the wavelength, we get 2L equals the wavelength. And then the frequency itself, if we remember V equals frequency times wavelength, frequency is just V over the wavelength. So this is V over the wavelength, which the wavelength is 2L over N, so this is 2L N times V. It flips because the wavelength's in the denominator. And then when N is 1, you get a fundamental frequency of V over 2L. Then we can do the same thing here. Right? In this case, the wavelength is going to be equal to the length itself, since one whole wavelength is the length of the chord. And so that fundamental, the second harmonic frequency is going to be V over the wavelength, which is NV over 2L. I'm sorry, I have a little error there. That's not supposed to be 2L. Wavelength I said is L. Right. And so this is going to be 2 times V over L, since this is the second harmonic. And so this is V over L wait a second here. Yeah, it's supposed to be there. 2L over L. Oh, I see what I did. Okay. Okay. Let me kind of step back a second here. Okay, this is where the N comes in. We can actually get the N with just looking at the wavelength. So this wavelength is 2L over L. Okay, so make that 2L over, 2L over 2. Okay, so the same thing as wavelength equals L, but we're going to add this 2 over 2 in order to get it to kind of match up. And so when we put it in, we get 2L over 2 times V. Okay, which still matches, where is it? This equation. Our N is just 2 here. And then we have the 2L on the bottom. So this V over 2L becomes 2 times what we have here. So 2 times the fundamental frequency, or F1 as we want to call it. And then we can do the same thing with 3. The wavelength is two-thirds of the length. And when we go look through, we get that the fundamental frequency, the third frequency is the fundamental frequency times 3. And the same works from that point on. 4 times fundamental is the fourth one, and so on. So our frequency for any overtone is equal to N, which is the harmonic, times the fundamental, which I'm just call F1. Alright. So there's many kinds of balance systems, especially music. String instruments all have a balance system. Soundboard has a balance system. A bridge will have a balance system. Even a jump rope has a balance system. Right, so if we are looking at a violin string, and it's going to vibrate at 294 hertz, when unfingered. Right? At what frequency will it vibrate if it's fingered 1/3 of the way down from the end? Right, so this 294 is what we call that fundamental frequency. And then we want to find the how much it'll be fingered if it's one, or how much the frequency be if you put your finger 1/3 of the way down. Right, and so we can write this frequency, new frequency, as velocity over 2 times 2/3 of the length, since you're switching the closed system and now you have a different closed system. And so we end up with let's see here, V over, see, the 3 will go to the top, so 3 V over 2 times 2L. I won't write it like that. So this times this is in the bottom, and then 3 moves to the top. And this V over 2L. Right, remember, fundamental is V over 2L. So that's which is in this case 294 from this. So this is 3/2 times 294, which comes out to be 441 hertz. And so that's your next or that's your fundamental frequency when you put your finger on it, and so you change the sound. Check the time. Alright, I'm going to finish this one problem, and I'm going to start the next video for it. Alright, so you have an oscillator here, has a rope attached to it, going over a pulley, and then there's a mass hanging on the pulley. This rope on the top is 1.5 meters long. And let's see, the oscillator oscillates at 60 hertz. So it goes up and down. String mass per unit length is 3.5 times 10 to the negative 4. And so what's important with that, let me start with that right there. The mass is 3.5 times 10 to the negative 4 times the length to get the whole mass. So this is kilograms per meter times meter will give you kilograms. Okay, so that's the mass. We're in terms of length. The string passes over a pulley, distance 150 meters away. Oh, sorry, 1.5 meters away. And the weights are hung from the end. What mass M must be hung from the end of the string to produce well, this goes into these parts. So produce 1 loop, 2 loops, 5 loops. Alright, and then we're going to assume the string at the oscillator is a node, which is somewhat true. Alright, so first thing we've got to do is find our velocity. So this is for A, and we'll move on to B and C afterwards. Alright, so A, we'll start with the velocity, square root of the tension length over the mass. The tension, if we think about this weight, and I'll draw over here. Actually, let me draw up top here. We have mass pulling down, we'll have tension pulling up. And so that tension is going to be equal to that mass times that weight. So the mass of the weight, me put S here for the string, mass of the string, times gravity, times L over mass of the string, and then take the square root. Right, so what we can do here is we can plug in for the mass of the string what we have here, 3.5 times 10 to the negative 4L. So you have mass of the weight, gravity, and then 3.5 times 10 to the negative 4L, and then L on the top. And so those L's cancel. So you have mass of the weight times gravity over 3.5 times 10 to the negative 4. Right? This weight is this weight here, mass of this thing. Alright, so now we're going to look at the fundamental frequency. This is NV over 2L. And in this case, N is 1. So we get, hold in the N for right now though. And so we have the velocity, so we can plug that in. So N over 2L times square root of mWg over 3.5 times 10 to the negative 4. And let's see here. What we want to do is we want to find the mass that this is operating on when it's at a one loop. And so this is when n equals 1, and we know that this operates at 60 hertz. So this is equal to 60 hertz for that fundamental, and n equals 1. So we can write this as 1 over 2 times L square root of mW times G over 3.5 times 10 to the negative 4. And this is equal to 60. And then we want to solve for mW basically. So we'll multiply this by 2 times L. So square root of mWg over 3.5 times 10 to the negative 4 equals 2 times 60 times L. And then we can take the square both sides. And this is going to be 4 times 60 squared times L squared. And then multiply by the 3.5 and divide by G. And so you get the mass of the weight is 3.5 times 10 to the negative 4 over G times 4 times 60 squared times L, which L is 1.5. So let's see, 4 times 60 squared times 1.5 times 3.5 to the negative 4 divided by 9.8. And we get mass is 0.771. Alright, so at this point, Well, I should have done that. I switched it, but I had n, the one here. This was your n. We would have had an n in the denominator here, which means the n would have been squared here. Okay, as we move through, and so you end up with an n squared being divided. Right, that allows us now to go to the next problem without really having to do all the algebra. We just know that this is going to be n squared, which is going to end up being 1. So now to do part B, for that mass, we get 0.771 over 2 squared. 2 loops, 2 squared. So 0.771 over 4. Which is 0.193. And then for C, that's 5. So we do the same thing in mass as 0.771 over 5 squared. Right, which is 0.0308 kilograms. Okay. So we just need a smaller mass each time to get it to vibrate at a higher harmonic. Okay, so I'm going to stop with, I think this is the end of that problem. Let me just double check. Yeah. Okay, so I'm going to go into the energy transported by waves in the last video. That would then end the semi-harmonic motion. I will probably take as far as long as I need to. If you have any questions, of course, just email me. I'm not to get my dog breakfast before I do the next video, but I'll see you in the next video. Alright, bye.